With our new full understanding of the gravitational force, perhaps we might expect a fuller understanding of gravitational potential energy to follow, because that was based off the gravitational force when we derived it in Lecture 7, if you remember. We said in Lecture 7 that the gravitational potential energy is expressed this way. U grav is equal to mgy. Yet, the gravitational force on a body can be expressed more generally now as this. Force is equal to the gravitational constant, capital G, is the mass of, we'll call one of them the Earth, times the mass of the other divided by the distance between them squared. And so for problems in which r changes enough that the gravitational force can't be approximated to be constant, we need a more general expression for gravitational potential energy. And we'll derive it in the same way we did in Lecture 7, but this time with a more general expression for force. We consider a body of mass m outside the Earth and compute the work done by the gravitational force as it moves toward or away from the Earth from point R1 to R2. So the work done by the gravitational force is equal to the integral from R1 to R2 F here, where this F sub R r being the position vector, is equal to negative gravitational constant, m sub e, m, divided by distance between squared. This minus sign isn't a mistake. It arises because we're considering down to be negative, and the force on the body by the Earth acts in the downward direction. So solving the integral, we get capital G. You can take these outside the integral. I always choose to do this around 5 o'clock, don't I? R squared. And the next step is we get the subtraction of terms. R2 minus the same thing, but with R1. And that's the work, right? Total work done by gravitational force. And so yet again, just like in chapter 6 and 7 with kinetic energy and various potential energies, we have this form where we have total work due to something being set equal to the subtraction of two very similar looking terms. And so we're going to take these terms, these terms, and we're just going to call it something, right? So that is the gravitational potential energy. And I'm going to write it here. Our new definition as a skinny u is equal to negative g. And if you're on the Earth, one of the m's is going to be Earth, but it doesn't have to be. But I'll write it that way. Oops, without the square. So there it is. Because the derivative of the potential should give you the force back. We didn't explicitly cover that, but it is there on the equation sheet if you're wondering what that was all about. Of course, if we're not talking about the Earth, m sub e is something different, whatever other planet or body is involved. As r decreases, the potential due to this gravitation decreases. It becomes more negative. So it's a little bit odd. We have this negative sign, and as r decreases, this whole term gets more negative, so it is also decreasing. This concept of things wanting to go from higher potential to lower potential will also be supremely important in electromagnetism when you start talking about electric potential, voltages in circuits and such. So keep that in mind. It'll give you a general template for going forward, going from potential to understanding what that might mean physically or otherwise. All right. So not quite done yet. I want to prove to you, so we went from this, or rather we went from, our original was mgy, and we went from this to that, and if we're talking about an object on the surface of the Earth, these two should be equivalent, otherwise I've lied to you, right? So let me prove that to you real quick. So first we will rewrite this here. Work. I'll put the little g there. Is equal to g. There we go. Mass of Earth m over r2 minus g mass of Earth times the other mass over r1. All we're going to do is we're going to find a common denominator. So we're going to bring these terms together, and you get g sub e m. You get r1 minus r2 on top, and r1 r2 down bottom. Since this is on or very near the Earth's surface, r1 and r2 can both be approximated as the radius of the Earth. The radius of the Earth, which I will write as r sub capital E. So we'll leave these up here for good reason, you'll see. But this here, radius of the Earth, I'll do capital R sub E. That would be squared, because these are each about equal to that, right? If you're talking about something 9 meters off the ground, but you're talking in terms of radius of the Earth, those 9 meters don't really contribute much, and we can approximate just fine. And earlier, our definition for g, lowercase g here, that 9.8, where that actually came from, we said that this was the gravitational constant times the mass of the Earth divided by the mass of the other body, r(e) squared. And so, if you look, we have that present. So this, and then this, right? And so if we sub in g for that equation, then we have the work grav is equal to mg r2 or r1 minus r2, where r refers to the height. Usually we talk in terms of height if we're talking about things just on the surface of the Earth. And we usually express that with y. So we can write mg, we'll say negative y2 minus y1. Right? And that means that grav is equal to mg y1 minus mg y2, right? And since we know that it is ug 1 minus u g2, right? It's a difference of two potential. Then we get that u grav, in this case, I'm talking about something on the surface of the Earth, is that mgy term here. right? So the more general case, if we go back to the specific cases that we were talking about, something on the surface of the Earth, on or close to the surface of the Earth, then we get back to our simple equation, where we were just taking for granted that this was a known constant and going forth with it. But now we know the true constant is this capital G, and the true full equation, which works anywhere in the universe. So that's about all we're going to cover for gravitation. Next would follow orbital mechanics, Kepler's laws, and the rest of astrophysics, but we will stop here. If you're interested in learning further topics in astrophysics, or astronomy, or planetary science, or anything else, I'd start with Kepler's laws, and there's plenty of other courses for you to explore these topics in. All right?